An agent is trained to navigate an interactive web environment to complete a query-based web task. The query can either be a structured query or a natural language input. An example of web task is forwarding an email from inbox. In this example, there is a natural language input, forward an email from Bob to Alice. Another example of web task is entering information in web pages. In this specific example, there is a natural language input, enter 7:35 a.m. and submit. Now some characteristics of web task. First is the high dimensionality of web task. A HTML web page has numerous constituent elements or tags that make it very high dimensional for an agent to navigate. The diagram shows a representation of web pages called DOM tree, which will be our input format for web pages. Second is the sparsity of rewards. The web navigation agent only gets a reward at the end on completion. This makes it difficult to get rewards for each action taken in a long trajectory. Third is the multimodality and variety of data present in web pages. The web pages not only have structured data but also have unstructured data, and also there is a lot of variety in the content. These characteristics also present some important challenges. The sparsity of reward leads to failure of standard RL algorithms like Q-learning SARSA. Also, to ensure broad coverage in high-dimensional tasks requires supplying a very high number of trajectory, which is impossible. This leads to failure of methods like behavioral cloning. The presence of multimodal data makes these web tasks significantly different. We have tried to solve these in our proposed solution. We use the workflow guided exploration method, in which we solve the problem of high dimensionality by training an additional policy that constrains exploration around demos through use of workflows. Workflows provide high-level actions, and the model is restricted in the choice of possible action given the current state and sampled workflow. These workflows, conditioned on demonstration instead of current state, allow the model to learn better representation instead of overfitting. This slide shows the demonstration, corresponding state action sequence, and workflow lattice. For each demonstration, the workflow policy builds a workflow lattice. Next, the workflow policy samples a workflow, which is highlighted, and further samples actual actions taken. Having a higher level workflow guidance helps sample actions similar to optimal action rather than any random action.
We show how the workflow policy and the neural policy get trained alternately. The workflow policy first samples a workflow and then samples an episode from the workflow. It adds the episode to the replay buffer only if it gives the positive reward. Training and episode rollout occur at every step for the workflow policy. The neural policy gets trained and rolls out episodes after every 10 steps. This process keeps repeating till the end of training. We use a single layer neural network with softmax outputs which decide the weights for every workflow step. Having sampled a workflow step as per the softmax weights, the workflow policy further samples an action from a uniform distribution where the probability of sampling every action is the inverse of the number of possible actions given that workflow step. The workflow policy is trained with reinforce and a baseline of 0.1. The neural policy is a sophisticated DOM-net as described in the work by Liu and others. It has an embedder module that captures both spatial and hierarchical information in the DOM tree. It also has an attention module that learns the relative importance of information extracted from the DOM tree and that from the query to create a feature embedding for a state. It outputs the policy distribution and an approximated value function. It is trained using the synchronous advantage actor critic algorithm. As an extension to our baseline approach, we implement reward shaping in the form of reward augmentation to mitigate the problem of reward sparsity. We compute a potential function for every step and take the weighted difference between the potential for a state and that for the next state to decide the soft reward for a certain time step. The potential function is defined as the percentage of goal steps that have already been completed by the time the agent transitions from a particular state. We experiment with the email inbox and enter time task from the open source mini WOB++ benchmark. In email inbox, the agent has to complete basic tasks like forwarding an email and starring or deleting an email. For entered time, the agent has to enter a specified time on a web page. Our performance metric for all experiments is the running mean of the average reward with time. The average is taken over the rewards from 500 episodes and the running mean is computed over this quantity every 100 training steps. These are the results from the entered time task. The blue and the orange graphs plot our performance metric for WGE, while the green and the red graphs give the same for behavioral cloning. WGE trains and reaches nearly a running mean of 1.0, while behavioral cloning overfits and drops to minus 1.0. We also see a little improvement for WGE when we use more demonstrations. These are similar experiments for email inbox task, but we show the impact of reward shaping on performance. It looks like reward shaping offers some advantage when used with WGE. However, it's hard to infer any analogous trend for behavioral cloning. Maybe that's because behavioral cloning fails to learn the task at all. Also, the maximum running mean reached at the end of training is nearly 0.5, which is much less than 1.2 for enter time. This indicates that the email inbox task is more complex than the enter time task. In this experiment, we plot the performance of the agent for email inbox task when it learns from natural language queries. It is obvious that the agent is still able to run because of the presence of a powerful natural language parser in the pipeline. The parser converts an unstructured natural language query to a structured query. However, it is a bit surprising that the running mean again reaches a value of 1.2, although it is the same email inbox. Here are two short demos of our trained agent BS for the enter time and email inbox task respectively. In conclusion, we saw that workflow guided exploration outperforms behavior cloning for web tasks. Also, reverse shaping improved performance for WG.